Okay, thank you. My name is John Wise. I'm a professor at Georgia Tech, and I'm representing the Tempest collaboration, which is led by Brian O'Shea at MSU, and also our group members include Dave Collins, Cameron Hummels, Devin Sylvia, and Britton Smith. So I'll be talking about Milky Way-like galaxies, simulations of those, and their progenitors and their host environments. Talking about the first supernova that actually enriched the first galaxies, and also what are the connections in between the Milky Way galaxies, the satellites, and the first galaxies. So, Tiziana gave a good overview of cosmology, how galaxies form, but galaxies, they form through mergers, right? Mainly through mergers, and they evolve over several to 13 billion years of evolution. But not only do the stars actually evolve, but the supernova, stellar winds, they enrich their surrounding environments. And astronomers, they can probe this gas. You can divide it up into interstellar medium, the ISM, circumgalactic medium, CGM, and the intergalactic medium, the IGM, to actually probe what kind of metals actually are ejected from these supernova out into their environments. And these metals, right, if you actually look anywhere in the galaxy, look at any star, you see metals or any elements heavier than lithium. So here I show some work from Anil Frebel. Here's a stellar spectrum of the sun, and here are 3 metal poor stars. So you can see their absorption lines are much less prominent. So this last number is in log, right? So these are around 10 to the minus 3 to 10 to the minus 4 of solar metallicity. So can we connect these metal poor stars to when they're actually enriched, right? So these metal poor stars, they actually suggest an early enrichment from the first galaxies. And so can we actually use simulations to connect these first galaxies to Milky Way-like galaxies and their satellites? So there are a couple of ways to actually do this. We can actually probe very distant galaxies directly observing the first galaxies, or we can actually look close to our own home, right? Looking at dwarf galaxies. So next year, I took this picture, this was taken yesterday, the James Webb Space Telescope is very gorgeous with this gold plating. You can see how big it is. You can see her down there, 6.5 meters. It'll be launched in about a year and a half. So we can probe the very distant, not only, there are many other things that JWST is going to study, but first galaxies is one of the main targets. So we can use JWST to look at these distant galaxies, and we can actually use the Dark Energy Survey to actually look for the remnants or the relics of these first galaxies that are now orbiting around our own Milky Way. So a couple years ago, it discovered 8 new, what's called ultra-faint dwarfs. And these are fossils of an earlier time. So here, when you think of a galaxy, you think of some grand spiral design or elliptical galaxy that's red and dead. But what it's found is, so when it takes this field here, right, and you have to actually remove typical halo stars that are not part of any bound system other than Milky Way, and then what's left over is this ultra-faint dwarf. There's only 300 stars in this galaxy here. So this is a dwarf galaxy called Reticulum-2, and it's very special because it's enhanced by our process elements. And not only do we can look at galaxies, but we can look at the gas surrounding the galaxies in the CGM. So the CGM, they're around half of the baryons are not only in the galaxy itself, but surrounding the galaxy in the CGM inside this dark matter halo. But it doesn't emit that much light. What astronomers do is actually take background sources, like a quasar is powered by a supermassive black hole, and it shines through the CGM, producing absorption lines. So the CGM plays an important role in actually regulating star formation and feeding gas into the actual galaxy for star formation. And what we want to do, what all simulators want to do of galaxy formation is actually match observations. So here I just pulled 2 examples from Mark Voigt's paper showing, right, this is, you can think about this as dark matter halo mass versus the stellar mass, or stellar mass fraction, right? The blue are observations. Here's Mark Voigt's model. It's an analytical model. And here is also stellar mass versus metallicity of the stars. So that's the ultimate goal, to actually match these and explain the scatter. So, and to do this, we use, you heard about it yesterday, a code called Enzo. It's open source, community driven, and it has a bunch of physics. You heard it yesterday, it doesn't really scale much to around a few thousand cores, but it's physics rich. So in our simulations we use, we're still working on MHD simulations. We do hydro, non-equilibrium chemistry, radiation transport through ray tracing, and star formation. We don't include any black hole feedback. So we refine on multiple things like overdensity as usual, Jeans length, linearity, and the code itself, it's stable. If you use quad precision for time and position, it's stable up to 41 levels of refinement, but the simulations I'll be showing today will be anywhere from like 10 to 15 levels of refinement. And the simulations, depending on the actual simulation, we use anywhere from 8 to 128 nodes. So it's a moderately sized. We aren't running like super large simulations. But there's a lot to be learned from these moderately sized simulations. So we take two approaches. We both use isolated galaxy simulations as a controlled experiment, right, where we can actually control the initial conditions, and we can use that to actually tune our sub-resolution models for star formation. And also, we use that information that we take from these controlled experiments to actually use it in cosmological simulations. And I just took this is a formation of one of these first galaxies. You can see how intense the merger history actually is, and winds being blown out from supernova from these halos here. So to give you a sense, these are relatively cheap. They take like 10,000 core node hours, and these take around 100,000 to 250,000 node hours. Okay, first I want to focus on cosmological simulations. So to do this, we use a Pathfinder volume of 100 megaparsecs over h, and here I show the halo density, right? So what we do is we actually take this volume here and look for Milky Way-like galaxies. And we can get halo mass functions here, so it builds from high redshift or early times up to this red here. And we're looking for halos with around 10 to the 12 solar masses. So we have 8,000 halos that have that mass, but we know that the Milky Way hasn't had a major merger in the last 10 billion years. So we select the subset that don't have major mergers that are highlighted in green. Now we're down to 200 halos. And then we look at different environments, like average environments, overdense or underdense environments, and overdense environments. And we choose those halos to actually focus our resolution on and to do these what's called zoom-in simulations, where we have much higher resolution than the whole box itself. So here's one example that I show. So here is the mass history growth of the main halo. It ends up at 10 to 12 solar masses. These lines are the progenitors, or the other halos that actually merge into it. And we also look at satellite galaxies of the Milky Way. So these are the mass histories of these. And we also take a subset of these and go to, we're still working on this ultra high resolution that actually look at the first stars. We don't run it to very high or low redshifts, like redshift 15 or so, to actually see the first stars forming. Okay, so I want to show a movie that was very, I guess, privileged to have, but I have to give all credit to Donna Crocs and her group at NCSA for making this. I got Dr. Strange to actually say something.
Within the first 300 million years, gravity drew the primordial gas into filaments and dense centers. The first generation of stars ignited. Trillions upon trillions of newborn stars flooded the cosmos with intense ultraviolet light that heated their surroundings. Vast patches of hot gas intersected and merged.
So there you could see really stochastic star formation. And that orange was the hot ionized regions, these H2 regions that are being heated by the stellar radiation. And these first stars are very massive, so they're very short-lived. This is why you saw it be heated, and then it cools down through recombination. But this was previous work that was done a few years ago before our PRAC, and it was only looking at a very small volume. So we didn't really know what it turned into in the present day. And now we're working on these zoom-in simulations, where I actually made this on Monday, where we're actually, I just focused on two of these early galaxies that have a halo mass of 10 to the 8. So here, if I pause it, so here are two galaxies that we're looking at. So blue is cold, red is hot, and in the green here is the radiation coming out of these. But just to demonstrate how much resolution we can actually afford in these simulations, how we can actually resolve these molecular clouds that are around 30 parsecs across in 100 megaparsec, co-moving megaparsec volume. Okay, now on to the isolated galaxies. So what can we actually do with these, right? We can control a lot of things like halo mass, how gas-rich is the disk, what is the CGM initially like, what is the entry profile, and most importantly, how do we actually model star formation? Because we don't model how stars form because, I mean, that dynamic range is way too huge and too expensive and, I mean, unrealistic to actually do it at the current time. And also, we can have a lot of control over resolution. So we can do resolution studies, model studies, and so on, while exploring these quantities, like how does CGM actually look like compared to the star formation? How do the ejected gas actually fall back onto the disk? And how does it regulate star formation? So Devin Sylvia, he's run many different types of these isolated galaxy simulations, but I'm going to just show two of them. So one is a quiescent one. Here's a star formation rate. And in the same halo, he increased the gas fraction inside of the disk, and it boosted the star formation by a factor of a few or so. And this is run over 1.7 gigayears. So here are projections of temperature of both of these. So you can see, I mean, after this initial plume, but you still have all that star formation kind of pumping out energy into the CGM, and it becomes very turbulent. And in this quiescent one that has this lower star formation, you can see it's much less dynamic, right? And you can get these cold clumps forming here, and they eventually fall back down into the disk. Also, we can look at metallicity, right? All these metals that are being blown out by the supernova being ejected outwards, mixing with this initially low metallicity gas in there. That's one thing. We have to kind of ignore that initial burst to actually see what is the steady state of these simulations. But you can just see how fast the winds are in the starburst galaxy versus a quiescent galaxy like this. Okay, but all this suite of simulations allows us to understand what's the best model to fit actual observations, and what is the required resolution that we actually need. Because if we use typical refinement criterion in ENSO, or AMR code, right, based on density, we pretty much focus our resolution where the disk is. But if we want to study the IGM or the CGM, we can actually force a certain resolution around this galaxy itself. And I just want to show you, this is work done by Cameron Hummels at Caltech. So let me pause it, some interesting point here, but you can see just how much more structure you get in these clouds being formed. Right, if I just pause it there, you can see how smooth it is if we don't really control the resolution in the CGM, whereas if we actually force this resolution, we basically need to control, we need to look at how quickly the gas cools and how quickly this condensates into these clumps. But, I mean, all of this is nice and well, right? I've just shown like density, temperature, and metallicity, but you can't go out and observe that. So we have to, I think it's essential to actually, to turn these into mock observations, what the actual observers actually see. All right, this is where a code called, this analysis toolkit called Trident, which is built upon YT, goes in and actually generates mock spectra and images as well. So this is just a demonstration where you have some sight light going through a cosmological box with a random orientation, random position, just going in periodically through this box. And as it encounters dense clumps, it absorbs the intrinsic spectrum, right? So this is for neutral hydrogen, but we can do many elements, right? Because the CGM is very sensitive to what kind of star formation actually occurs in the galaxy. We can look at many different ions, right? We have magnesium-2, silicon-3, oxygen-6, and carbon-4. Because these are some strong emission or absorption lines that can actually be observed in the CGM through these quasar absorption lines, right? So you can imagine taking one of these halos here and tracing lines through these to actually get mock observations. And once you have that, right, that's only the first step. I mean, that's an ideal situation here. So what Trident actually does is, first it produces these absorption lines here and here, then it adds, so this is just some normalized spectrum here, then it adds the background spectrum, this flashlight here with these emission lines, and then you add the Milky Way lines, because the light actually has to come from that galaxy all the way to us through the Milky Way halo, add the Milky Way absorption lines, then you can add the telescope, I guess, resolution effects here and add noise. So we can actually directly compare with observations. Okay, so I just want to summarize saying that we've run a suite of isolated galaxy simulations where we can actually produce mock observations to constrain our resolution, our star formation prescriptions, because there have been there's been, I guess, this one main study that's been going on, the Agora galaxy simulation comparison, that actually showed that the numerical models don't really make a difference. It's these subgrid models of star formation. Because, I mean, just imagine you're injecting a lot of energy where, like, whether you run SPH, AMR, or moving mesh code, all that really doesn't matter in the end, where we have these subgrid models that are actually dictating what are the galaxy. I mean, it's really, I guess, sensitive to what are these subgrid models for star formation and black hole formation. And also want to say that these isolated galaxy simulations, they produce realistic CGM profiles and these out plumes of gas coming out of the disks and raining back onto the disk that can actually feed more star formation. And we're still working on, I mean, how do we actually connect these distant galaxies to the nearby galaxies here? And lastly, we're just all looking forward to ENSO-P. I mean, we have to kind of port all these physics modules into ENSO-P, but we hope to start in the next year or so. So thank you for your attention.